Hey, this is Horner. We're going to look at the next section for rotational motion. This one is a little bit different. So this one deals with some forces. So we've been through some kinematics of angular motion. Now we're going to look at some dynamics and see how this works. This is a kind of a popular ride that you can go to an amusement park and do. This one's tilted a little bit. We're going to assume that it's just spinning and that it's horizontal like this. And you sit on a swing out to the side here. So we need to do a few things. The first thing that we need to do is let's go ahead and do a free body diagram for the person, but we're going to do it over here. And we're going to say that that person is here. And we know that we have a tension in the cable going up and to the right like that. And then we have mg moving down. So we're going to put mg. So a couple things we need to do. One of them is let's get everything into a positive y and a positive x direction. So if we do that, we know that we need to have this, these two sides of the triangle, and we're going to go ahead and say that this is angle theta. It's the same angle as this one. We can also put it here if we want to. And if this is tension here, we know that this would be the t times the sine of the angle, and this would be t times the cosine of the angle. And I can do the same thing here. T cosine of the angle is the adjacent side, and t sine of the angle is here. So either way you want to draw this is absolutely fine. If you want to put your mg down here, you could. There's our t's, and you'll kind of see the same thing. They want us to figure out what is the maximum angular speed. To do that, we're going to do sum of the forces. Let's start with sum of the forces in the x direction. And that's equal to, now notice that the only force I have in the x direction here is t, sine of the angle, and that's going to be equal to mv squared over r. So there's our circular motion, centripetal force, and then here is one of those components of the tension that's going in the x direction. We need to do the same thing for the y direction, so sum of the forces in the y is equal to, now let's use this, notice we have t times the cosine of the angle going up minus mg, which is down, and those are equal to 0. And it's equal to 0 because this person is going in a circle, and they're not flying up and they're not flying down, they're just static at this point. Let's go ahead and solve both these equations for t. So t is equal to mv squared all over r times the sine of the angle. And this one is equal to t is equal to mg all over the cosine of the angle. Now for this one, it says angular speed, but remember v is linear speed. So if I want to go from one to the other, I know that, here, let's do this in blue, the velocity is equal to r times the angular speed. So if I want to switch it, I'm going to need to convert this to angular speed, and if I want that, I'm going to need to do the omega squared times r squared. So I'm going to take this and I'm going to get rid of the v squared, and I'm going to do omega squared times r squared. You'll also notice that I have an r already on the bottom, so I'm going to get rid of the square on the top, and I'm going to rewrite this one. T is equal to m times omega squared times r all over the sine of the angle. And then here I've got t is equal to mg over the cosine of the angle. If I substitute this in for t, I'm going to have mg over the cosine of the angle is equal to m omega squared r all over the sine of the angle. So let's get rid of the m's. The m's can go away. We're going to solve for omega squared, so we're going to say omega squared is equal to, and then we're going to have cosine, we'll have cosine on the bottom. We're going to have sine on the top. We still have g on the top, so this will be g times the sine of the angle all over r times the cosine of the angle. We also know that sine of the angle is equal, sine of the angle over cosine of the angle, so this right here is equal to tangent. So this would be g over r times the tangent of the angle. But we need to figure out what is r because we don't have an r here. If you think about it, r would actually be, and we'll do this in purple, r would be the distance from here all the way over to the middle of the pole. So we already have x. We need to figure out what is this side. Well, we know that we have L here, so this side of the triangle is going to be L times the sine of the angle. So r here changes. This is going to be equal to g times the tangent of the angle over, now we're going to have x plus L sine of the angle. X plus L sine of the angle. The only thing is that's for omega squared, so we need to get it just into terms of omega. So now our very last step is omega is equal to the square root of g times the tangent of the angle all over x plus L sine of the angle. And that would be our final answer after doing all of that algebra / physics.